next seminar, the webinar in our series for the Computational Social Sciences of America. We are very honored to have Dirk Helbing here. Dirk Helbing is from, I always say it's ETH Zurich. So a discovery I hadn't realized was just there is quite a lot of ABM going on at your university. I mean, there's a lot of names that go down across the field, which is amazing. So it's I feel like you're becoming where you are is becoming quite a large hub for agent-based modeling and simulation. But Dr. Hebling is expert within transportation, specifically pedestrian transportation. So what we're going to do today is we're going to do our normal webinar format, which is I will have 30 minutes to ask some formal questions, or roughly that amount, and then we'll open it up to the floor. So what I'd ask is for people not to ask questions until we've reached that 30-minute mark, and then we promise that we will give you time to ask all the questions you guys like. Okay, and then usually we finish within the hour. All right. So without further ado, thank you, Dr. Helbing, for being with us today. Really appreciate it. So you're coming from the transportation world. I mean, it's a huge field, right? So, to me to turn around to you and say, hey, explain ABM in transportation would take hours and hours and hours and hours and hours, right? But you come from particularly on focusing on pedestrian dynamics. Can you sort of just give us a bit of an overview of your domain, how you see it fits into the larger sort of ABM research community?
I have actually a physics background, and I was studying in Göttingen, Germany at that time. And there were some protests, and somehow this activated me to think about social phenomena. I was really keen to combine physics with sociology or social sciences all together. I was looking for a subject that would basically be at the interface of the two. And I came up with three subjects I was considering for my diploma thesis at that time. One was arms race. Another one was on a group formation, group dynamics. And the third one was pedestrian flows, because I'd observed that pedestrian flows somehow remind of fluid flows in certain conditions. And I thought perhaps physics can help to understand this better. And so I chose to model pedestrians, actually on three levels. On the, as we call it, microscopic level, actually individual level. So here we go, agent-based modeling. I'm not sure I used that word at that time. It was around 1990. And I was coming from the pedestrian literature that I read at that time. So it was transportation planning literature, among others. And it was difficult to do those simulations because computers were so much weaker in terms of CPU, but also in terms of memory. I really had to use the computer screen's memory in order to be able to simulate 500 pedestrians. Now, it sounds ridiculous today, but this was the only trick that helped. So it was basically GPU computing. I also was developing gas kinetic models and deriving from those fluid dynamic models. And the idea to use such kind of models has been around. So, for example, Henderson has published two little contributions, little in terms of size, lengths, to Nature at that time about pedestrians. I was interested in the Boltzmann-like distribution of speeds. And in a fluid dynamic journal, he also proposed fluid dynamic equations. But he basically assumed that physics equations would be transferable directly to pedestrians, and I doubted that because a couple of conditions that are underlying those equations were not met. So in physics, you have momentum conservation and you have energy conservation when two particles interact with each other. And that is not true for pedestrians. So I was deriving modified equations that would take into account that particularity of pedestrian interactions. And I should say, the partial differential equations that came out of this look horrible. So I kept doing the agent-based simulations, basically. And those were based on the idea, also inspired by physics, that we could transfer a force-based approach to understanding pedestrian interactions. And so the social force model was born.
Yes, and I've used it myself. It's fantastic. I didn't realize that you also did. Well, we're looking at group formation as well. That's pretty cool. So that's something else close to my heart. So how do you? I mean, so this work here. I mean, like I said, I've hinted at earlier. So given the background on how you got involved in social force dynamics and the pedestrian world, how do you see the pedestrian agent-based world fitting in the larger transportation simulation world? I mean, is this, is it, is it to the side or is it integrated in the middle? I mean, because I know there is that difficulty in simulating multimodalities. I mean, a lot of simulations tend to assume there's pedestrians over here and then vehicles or whatever else over here. So how do you see it all fitting together in your opinion?
Yeah, perhaps I should continue saying that after my diploma thesis, I was changing to the city of Stuttgart in Germany, and I was working with Wolfgang Weidlich. He was one of the few social physicists at that time. And I did all sorts of things like opinion modeling, modeling of migration, game theoretical models, and stuff like that. But people wanted me to continue on pedestrians. Then I worked on trail formation, among others. But after my completed PhD, I had to change subject a little bit. And this is when I started with traffic flow modeling. Methodology is similar. Phenomena are in part different. Both are very interesting systems where collective phenomena matter that people, would not necessarily expect, like the lane formation in pedestrian counterflows, or even more interesting, the stripe formation in two crossing pedestrian flows, or the crowd turbulence phenomenon that causes crowd disasters sometimes, unfortunately. So, yeah, with my habilitation thesis, this is an additional thesis after the PhD thesis in Germany for some time. I think it's not anymore what people do. It has been replaced by junior and assistant professorships, tenure track positions, basically. I modeled traffic flows, and later on also got interested in modeling traffic control, traffic optimization, including traffic light control. Traffic modeling has been using different kinds of modeling techniques actually since the 50s of last century. Now, as soon as computers became available, the issue of traffic control, but also traffic modeling, became of interest. And you may know fluid dynamic approaches such as the Lytle-Wissam or Lytle-Wissam-Richard model, and their microscopic car following models, microscopic in quotes in a sense, it's really a focus on the driver vehicle unit and its behavior. And the kind of model that is best to be used really depends on the question. So if you want to do kind of traffic forecast, traffic prediction in a large network of freeways, then a macroscopic model or a cellular automaton model would be suited because of the higher numerical efficiency. However, if you were interested in adaptive cruise control systems and automated driving, so very modern subjects, obviously, because we are now having autonomous cars introduced into traffic flows, then the microscopic models were more adequate because really you had to take care of accident risks and whether the acceleration behavior of cars would feel natural. So drivers would really like that technology. They would feel it comfortable. And it would also be, as I indicated, it would also be safe. And so really depending on the question, you would use different kinds of models, but ideally there would be a macro link. So you could basically derive equivalent macroscopic equations from the set of microscopic equations that you would use if you're interested in detail. So there's theoretical consistency, there's a logic behind this, right? So it's a lot more than parameter fitting as we would have it today when we use a data-driven approach and machine learning basically to try to fit those data as closely as possible. I'd like to mention just one interesting example. So people recently are using machine learning a lot in order to fit or even predict pedestrian trajectories. And those machine learning models actually work often better than the equation-based models, such as the social force model and also others. But it's no surprise because they contain a lot more parameters, right? If you're interested in how much can one parameter describe, then the social force model is doing pretty well. Now, the interesting point is machine learning models can predict trajectories much better, but they are missing the main point, namely to avoid collisions. So you can feed them as much data as you want, but they're not making this abstraction that what is really behind this is trying to avoid bumping into other people and keeping some distance. And perhaps with supervised learning, you could eventually get the machine learning to take care of that as well. But just a data set and machine learning unsupervised would not get the point.
So yeah, so actually that leads quite nicely into this question I got here. So in my experience, civil engineers, the transportation, folks that are running a lot of the research are almost anti-human factors, right? One classic example I always give is that, the highway capacity manual in the US, admits that, 50% accidents are caused by human error. Yet its whole section on traffic accidents is about the physical layout of roads, et cetera, et cetera. It's not talking about the human factors side of this. I mean, obviously your work when you're talking with pedestrian dynamics is human factors, right? It's literally humans moving in what else. Did you find in your career, did you get much pushback at all from what you were trying to do from the sort of like wider transportation community? And how did you deal with that?
No, actually, not so much from the transportation community, I would say. I think there was pretty constructive interaction with the transportation community, as far as I recall. There was more kind of a skepticism of social scientists with regard to physics-based or physics-inspired approaches. And it has often been criticized as physicalistic, perhaps not so much even the models that we have published about, because they're capturing really some interesting phenomena and also surprising phenomena, that self-organization that happens in pedestrian crowds. And even a model with just 2, 3 parameters can describe many different phenomena without having to take different parameters for each phenomenon. So it's really a powerful model to get a qualitative understanding of why certain things happen, which a machine learning approach doesn't give you. And as you may know, later on, while I was starting as a physicist, I was actually joining a faculty for transportation. And I wouldn't have gotten this professorship if they thought it was not relevant what I was doing. So, and there we also started doing our first experiments, game theoretical experiments, and also some pedestrian experiments. And eventually I got this professorship at ETH Zurich for sociology, in particular modeling and simulation. That was back in 2007, as you may know, these foundational papers on computational social science, which is now the name of my professorship, those were written in 2009. So I basically was working on stuff that did not even have a name in the beginning. Eventually, it was called social physics, traffic physics, this kind of stuff. And it developed eventually into computational social science, thereby getting a lot less physicalistic and more driven by the questions that social scientists themselves were raising. Also, teams became a lot more interdisciplinary. So, over the years, we had in my team a range of people from mathematics over physics, over biology to sociology, I think also psychology. Ethics mattered as well. Data science mattered. Experimenting in labs, in online experiments, even in real life settings in real cities, that all was added. And so it's, there's not so much physics in it anymore. And you may also know that we've done this cognitive model of pedestrian behavior together with Mehdi Musaid. So it's a heuristic model with 2 simple rules plus a physical interaction when people come too close to each other. And that was a bit surprising to me, I should say, because we always thought very much in the physics spirit, let's keep it simple, stupid, in the sense that let's keep the model so simple that it contains only a few parameters. Because if you have a model with many parameters, you can basically fit anything. So physicists would say with 3 parameters, you can fit an elephant, and with 5 parameters, you could make it wiggle with its tail. It's like, and then basically the question is, how much do you understand really if you can fit anything? And that was one of the reasons for going for simple models. And for a long time, we were keeping a distance to the cognitive level, even though I do think we have experimented with this a little bit. You could have pedestrians learn from scratch. I do think we tried something like that back in 1998 or so. Didn't publish much about it. So what happens now is a lot more advanced, of course. But adding vision and social behavior, that seemed to be making everything so much more complicated. And so we thought at least 10 more parameters would come in. and that's why we didn't do that at that time. And then Mehdi came over and said, I believe in heuristics. And he told me this example of how to catch a ball. So if you want to catch a ball, you're not following the trajectory of the ball, then extrapolate the parabola of the flight that this ball is taking, figuring out where it would come down, do all the integration, solve the mathematical equations, and once you've found the solution to this equation, you start running to that place. No, we don't do that. It's much simpler than that. You just need to gaze at the ball and need the angle constant. And then basically the ball will fall into your hands almost automatically. So there's a simple rule. This is just this angle that needs to be kept constant. And so he said, I want to come up with models that are as simple as that for pedestrians. And then actually we did come up with such a model, the cognitive pedestrian model, and it was basically two rules: hunting for gaps and keeping the time to collision above a certain value. And that worked pretty well. So there are two equations for this. It doesn't contain at all 10 parameters. And I found that very interesting and inspiring. And of course, we could add now all sorts of things, like when people are walking together in groups. In fact, there is a paper about this, and there was a surprise because it's anti-stream-like, it's anti-aerodynamic, I should say, because the group is bent forward like this, rather like that. And this is because people want to talk to each other, and in order to talk to each other, they want to look into each other's faces in order to see how the others respond, right? And so that is a stronger force than the kind of fluid dynamic, aerodynamic effect by kind of having to walk as a group against a crowd of other people. Of course, at very high density, things may change. But anyway, so there are certainly observations where we can find that social, psychological, cognitive factors do dominate, but in many cases, a social force-based approach is surprisingly successful to get kind of the main things right.
Excellent. So, okay, yeah, absolutely agree. So that's very interesting to hear that that you found more acceptance within the transportation community than the social science community. So I've only got a few minutes left with you, and I've got a ton of questions, but I will have to ask the obvious one, so we at least make sure this is covered. You talked a lot about your background and how you were involved in the evolution of this sort of like world of pedestrian modeling, especially within the macro world and the wider transportation world. Where do you see the future of all of this? What's the next big iteration that you think that's going to happen within the sort of like that community, that ABM transportation community?
Okay, that's a good question. I do think agent-based was on a very good way, on a promising way, and then it was kind of pushed away really by machine learning and AI to quite some extent. And so today people don't want to spend much time on thinking about what goes on between people or cars and bikes and whatever, politicians, CEOs of companies, whatever. So it is a lot more comfortable. You take a huge data set and feed it into machine learning and then go for a cup of coffee or kind of 100 cups of coffee and let the system figure it out. And it will come up with approximation that may look impressively realistic, but it's still more a computer game than a scientific model, I would say. And mostly it's a black box model, and you would not understand why certain things happen. I know, and if you would go then to another country, it's not entirely clear whether that model would really describe what people are doing in that country. There's different culture. People in Japan, for example, walk on the left, and so the social force model and the game theoretical models I've been working on can handle this. We can understand why in some countries people work on the left. That's even predicted. But a machine learning model that you feed with data from one country, lots of data, would probably not be able to handle that at all. So yeah, it looks impressive in the first moment, but then it's perhaps more deep fake than scientific model. And I think this risk is particularly big in areas where people are interested in complex, dynamical, networked systems. And even more so if there are delays and there are probabilistic effects in the interaction. So there are limitations of what can be learned by means of machine learning. And despite all these problems, I think what has really been tried is to build a digital twin of planet Earth, including all of its people. And the idea here is that you would basically treat people like machine learning black boxes that you feed with surveillance data. And it's one of the reasons why companies, secret services, and militaries around the world are so keen in collecting so much data about you. And it's a lot more data than you could even think about. And so they're training those black boxes basically to behave like you and can be used to manipulate you. And it's being used also in hybrid warfare, in information warfare. And I think it's dangerous for us. It's making us vulnerable because it's not just one country that can do that or one company. Basically, everyone who collects lots of data about people is now trying to build a digital twin. And in many cases, the digital twin may be right in its predictions, but also in many cases may be wrong. And then you're being punished perhaps for something you've never done and you would never do. And brings us also to predictive policing and all that kind of stuff. So slippery slope. Yeah, so this is basically what is happening, or perhaps what has already been happening, and which explains why the field today feels so much different from, say, 10 years ago, even though it looks still very similar to 10 years ago. So in fact, in the background, there's algorithms driven by big data that interfere with the real world in many places, and we don't see that and we don't feel that, but still it influences what happens in the world. And I do think it's dangerous because, among others, not only we're losing freedoms and agencies and things that are very concerning, I believe, but also I think this black box approach is a lot more limited, and particularly when it comes to complex dynamical systems, to human behavior, human brains, in a sense. Then in these cases, I think the black box approach is really limited. And the danger is that it would recommend action that would be producing quite some damage individually, collectively, socially, societal-wide, globally. And we've written a paper about revisiting the big data optimism, which is looking into those cases where things went wrong. And in fact, for every company, basically, there are really, in a sense, some big cases, you may call them scandals, where big data has done things terribly wrong. But there's not much talking about it. Somehow they got us distracted from it. But there is a cost of this black box approach. And this cost is probably much higher than has been assumed for some time. So what I believe will happen is that we'll see the machine learning approach fuse with the agent-based approach, a model-based, an equation-based, or logic-based approach, where we have underlying equations that can be understood. So there's some logic in what happens and why. But the parameters in these models would be fit using machine learning. And so I do see that combining the two approaches, perhaps also in the sense of pluralistic modeling, like having model-based approaches on the one hand, agent-based approaches on the one hand, and the machine learning-based approaches on the other hand, combining the two approaches in the sense of pluralistic modeling would also give better predictions, I would say. Perhaps when it comes to hurricanes, there is a desperate need for prediction, and no model is really 100% accurate, but there are several models, and what people often do is they run all of them, and then they average over them, and it turns out that in many cases that gives you the best prediction.
Thank you. So a controversial topic you brought up towards the end. So I think this is probably a good time to let the audience come in and actually be part of this. So yeah, I will say, obviously, there's my student would kill me if I didn't mention explainable AI is a potential solution to some of the black box issues, but it's still in very early days at the moment. So what I'm going to ask the audience to do, if you've got a question to start with, can stick your hand up, as in you can use the little feature at the bottom, or to start with, if we've got no questions, you can just go ahead and start speaking. So anybody in the audience, do we have a question for Dr. Helbing? Don't be shy.
I see.
Oh, yes.
There.
Claudio, go for it.
Okay. Good evening to you, Dirk.
Hello.
I guess it's late afternoon. I really didn't want to be the first one to ask a question, but rather than keep everybody waiting here, I'm really happy and very excited to hear about the solution you just summarized about this conundrum, because I think it's in the end it's a very healthy scientific approach, a truly scientific approach to re-steering in a proper scientific methodology direction an enterprise that can otherwise go into very strange places, let's put it that way, undesirable in my view. So in terms of, I agree completely on that. What I am curious about is how do we plan our teaching, and how do we plan the design of what computational social science is about in light of this challenge? Because at the end of the day, we're around for a few more years and then that's it. But there are generations ahead of us that will continue to do this kind of exciting research. So how do we integrate these ideas in a formative sense? How soon, how early in scientific education should this come? And how does one start promoting that in the trenches, as it were, in the classrooms and in workshops and so forth? I think there's a very valuable role that perhaps even the CSSSA could play in this regard, and the European and Asian partners, of course. Thank you.
All right. Yeah, you mentioned a very important point here. I do think students now learn a lot more about data, in particular big data, about machine learning, AI, and they're really fascinated by this. So I think this should be part of the education, but it should also work out where things can go wrong and why. For example, we do have a data science course where we focus exactly on that. And here it's really important to make people aware that no measurement is exact. There's always some variability, and there are confidence intervals that are finite, and the parameters could be anywhere in those intervals and even beyond. And there's the phenomenon of sensitivity. So a little change of a parameter, perhaps just one parameter of many, could make a huge difference eventually. Important, for example, for pandemic prediction. There's a lot of uncertainty. This needs to be understood, and how to then respond to the fact of uncertainty and how to communicate that also to the public, to politicians, and so on. How do we deal with that? And I think it's important that once people see not only what can be done, wonderful things, of course, with machine learning and big data, that they would but also see the limitations of the approach. And then you would introduce to them the old methods like statistics, agent-based modeling, to basically show them these are complementary methods that can be used in combination with those new methods that are now basically trending, I would say, overhyped even. That they learn, they need to know also the old scientific methods in order to be able to judge the outcomes of machine learning and AI, and also to improve the outcomes by combining methods with each other. And yeah, I would start with big data and machine learning because that's what people expect now, and then as people basically get their bloody nose when facing hard, complex problems, rigged problems, then they would be more motivated in looking into statistics.
Thank you. So Doug's got a follow-up question as well, so I'm going to hand over to Doug.
Thank you. How do we get better about identifying when the learning set for an AI or an agent-based model has been insufficiently diverse? You get an AI that's very, very confident about what it has learned from what it saw, and the exception it never saw turns out to be fatal. But you don't know that until you encounter that exception. What can we do to be a little bit more robust against that phenomenon?
Yeah, I have perhaps an unexpected answer. Perhaps it's not even desirable if things are absolutely robust, because I tell you this, innovation will basically always be able to question a system that's based on old data, right? On previous data. Innovation will change the past of history potentially, and it should be able to do that. As soon as basically we could contain that, we would be in a danger of eventually ending up in the digital matrix, in a system which is kind of completely predictable and completely controllable. But yes, I'm getting the point. Of course, we should be aware of the limitations of models and also of data sets. And it's sometimes pretty shocking and also insightful that if you add or subtract just a few data points, the outcome, the behavior of the machine learning model could change dramatically. In some cases, at least, even if you use another hardware and the same data set and the same algorithm, which shouldn't be the case, because we've been educated that those things shouldn't matter. So this is obviously pointing to sensitivity of certain models, and to some extent we can understand what kind of models are sensitive to the data set, and I'm not sure you can always find a big enough and diverse enough data set you could eliminate the sensitivity problem altogether. I doubt that. But even if you don't have a sensitive problem, it could be that the data set falls short. Yeah, I can see that. And I think importantly, really, we need to always emphasize that a data set needs to be diverse. Diversity is an asset in a sense, for the quality of a model. It's also an asset for collective intelligence. It's an asset for markets. It's an asset for democracies. It's an asset for science. It's an asset for innovation, and it's an asset for resilience. So not just for the robustness of models. And I think it's good to work that out, why diversity can improve the outcome, and why therefore we need to make an extra effort to make sure we have it.
If I might follow up, one of the things we tried in my group was get the model to tell you a story, reduce your result in story form, and then run that by a couple of experts, because they may have trouble interacting with model input, model output. But if you tell them a story, is there anything about this story that just doesn't ring true to you? That seems to be more effective at identifying the things you've missed.
Yes, I agree with this. And for similar reasons, I have often been interested in visualizing what happens in the system, in an animated way. So it was perhaps natural and simple for pedestrians, but anyway, at that time, not everyone was doing that. So it was certainly helping to communicate what was happening in the system. And I often recommend that also to my students. If we can develop an intuition that can help us ask follow-up questions and explore a model, particularly a model with many parameters, if you want to find the interesting stuff, and if you have a huge parameter space, it's not so easy to find unless you have some intuition what could happen under what kind of conditions, right?
Thank you very much.
Also,
oh, sorry, go on.
Yeah, just waiting for the next question. As soon as the hand is up, I will stop talking. Until then, I just mentioned that I've done some projects together with companies, and the way I've been doing it is not just making phone calls or video calls and writing emails, but I always have a look at the system we're talking about to get really a personal impression, get some intuition about the system. And people have been contacting me based on, for example, the pedestrian work, even though they were interested in logistics. So it seems like this is something totally different. But they could not solve their problems, even though they had very, very skillful engineers with degrees, and somehow their conventional approach was facing limitations, and they needed to have another perspective. And in fact, it often turned out that the problem was different from what they thought it was. And then it was possible to come up with novel solutions that was really improving the performance of those systems, and they were very happy with that.
I would, yeah, I mean, as an operation researcher by background, that's one of the jokes that we always say, is that our job is to go in and tell you what your actual question is, right? You know, so it's, but it's, I mean, it's so true. I think there is, I think a lot of human stress is caused by not being, you know, not actually trying to answer the right question. So
I would not even want to judge whether a question is right or wrong, but I really think that once you ask a question, it's typically more or less straightforward to answer it. It will take some time. We'll find a way to find an answer. But are we asking the right question? Are we asking the interesting questions? Should we ask different questions? You know, I think asking questions is at least as important as answering questions, and as scientists, we should never forget about that.
Absolutely. So I know some people, the Zoom can be a bit of a pain with the figuring out where the actual raise hand thing is, but has anybody else got any questions? We've got about 10 minutes left, so got time for a couple more questions. So please don't be shy, just unmute yourself and ask if you like. Go again. Yeah, go for it, Doug.
All right. Well, on the question of redefining the problem, about 20 years ago, when Informs, the American Operations Research Society, decided to have this certified analytical practitioner test, they circulated to a number of people, can you give us some questions we could use? One of the ones I came up with was, how many times in a typical project do you redefine the problem? One of the alternatives I offered was never. If you get it right in the first place, you never have to redefine. And what I suggested was that anybody who chose that answer should not only fail the test, but should be kicked out of the profession.
Yeah, I mean, we have seen this reproduction crisis in certain sciences, and it has led to the consequence that now many experiments and many papers, many studies are pre-registered, and I think it's a good idea. So people would not basically adjust the question later on to something that they find. I think we should be honest about the way we learn about systems, about how we gain our insights, and also be honest to say if something didn't work, because we can also learn from that. And this is typically underreported, kind of the failed attempts. And that should be documented much better, because it would avoid that many people do the same thing, believing that nobody has done it so far.
How many pedestrian dynamics studies did you see that went along blithely looking on a physical model until somebody finally admitted, oh, by the way, avoiding collisions isn't good enough. You have to avoid getting within a certain distance of colliding, because these are people and they don't want to brush past each other. without colliding. That's not an acceptable situation for them. Where for granular flow of particles, it works fine.
Yeah, it really depends also on the situation. Now, in fact, at music events, for example, it could easily happen that densities get so high that there is bodily interaction, unintentional in many cases, but this is also where things can get dangerous. But actually, from the very beginning, we have distinguished between physical forces, social and psychological forces, forces in quotes, in a sense, like because they were representing the desire to keep some distance and also to feel more comfortable. I think that was in the back of my mind from the very beginning, because I had not only read physics books, but also psychology and social psychology and social science books. And I was interested in both, and that helped.
Okay, thank you. Anybody else got some questions? I've got a few ones here myself, but I just wanted to open it up. Good. Okay, so one of the things I found fascinating in transportation, and you mentioned this earlier, this idea of the micro simulation or micro stimulation, and that terminology as in micro, meso, and macro. And then, but I've been to TRB, Transportation Research Board, in the conference, and there are people that I think are doing agent-based modeling, but refuse to call it that. They insist on it being called microscopic modeling, microscopic modeling. Why do you think there's this conflict of terms? Why do you think there's this terminology tends to get convoluted and etc. And these almost camps of individuals in these different terms.
Yeah, so it's often related with people coming from different traditions and backgrounds and different scientific communities, and but also sometimes you say every 30 years, every generation, people reinvent things, just different they do the same things but with different methodology and find similar observations or so. Perhaps this is happening over here. I always found I do remember the times of those camps, because when I started, I was interacting also with social scientists on their conferences, and I do remember that the people who did agent-based modeling in the social sciences, being social scientists, they felt excluded actually from their social science colleagues. And in a sense, it was a bit similar in physics. So when I did the pedestrian modeling in the beginning, nobody knew what kind of field that was. Was it physics? No. Was it sociology? No. It was something in between. And eventually it turned out that both physicists and social scientists and biologists and engineers and roboticists took an interest in this, so it did not matter really whether it was this or that. There's something new was emerging here, and I'd like to talk in particular to the hearts of junior scientists here, because when I was starting, I was not sure whether there was a future of what I was doing, whether there was a career I could make, there was a position for me that I could get. Not even the professors that were supervising me could tell me this. I was taking a big risk, but I had decided that I wanted to do what I found most interesting because it would engage me most. I would be most committed. I would be working harder. I would be doing more fascinating stuff. And that was a real risk, and it takes time, and you need confidence. But it was paying off, I would say. Just don't lose faith. Also, sometimes interesting questions are right in front of your nose, and nobody ever paid attention to it, Like, of course, people have been walking in lanes in opposite walking directions for ages. Just the traffic engineers did not pay much interest in this. That was ignored until I saw that was interesting. It was symmetry breaking phenomenon, pattern formation, self-organization. Something somehow unexpected was happening, particular if you'd assume that there was a 50% chance to go to the right and a 50% chance to go to the left. So if the models were symmetric, then kind of this phenomenon was most interesting because it was not natural to happen. As soon as you assume a symmetry, which actually exists in the real world, then it's not so surprising anymore that you get lanes. But it's already an outcome of a collective learning process, a behavioral convention that basically has formed earlier, and we can understand that also based on models.
So we have a question in the chat from Milton. I don't know, Milton, if you wanted to ask that question yourself, or I can read it out. I don't know if you have the communication device. Okay, I can read it out. So the question is, has your work on pedestrian modeling social physics integration with route choice research of vehicles, i.e., travel time, number of turns, congestion, reliability, routes, familiarity, etc. So, and also, what are the issues of adding social forces specifications into a data-driven model?
Okay, so let's start with the first question. And obviously, there are colleagues who've been integrating route choice components. My team has done a little bit of work on this, not extensively, but choice models was part of what I was interested in, what I was doing. Today, there are actually quite a few simulation suites that people are using in order to, for example, assess safety of infrastructures or events. And it's being used in transportation planning. This is typically software that is multimodal. That means you have a simulation of cars, buses, and trucks. You have a simulation of public transportation. You have a simulation of bikers, and you have a simulation of pedestrians. And you would now have to add scooters too, right? And you can add logistics as well. So there are simulation tools that basically combine it all. So this is what you can make money with if you're interested in doing practical work. And it has made its way from science to application, you could say, of course, with adding details and adding parameters and sophistication. But yeah, science made the beginning, and it's one of those models you could say is useful. George Box's quote, all models are wrong, but some are useful. And I would say the social force model has turned out to be one of the useful models, even though it can be extended and made more detailed and sophisticated in 1,000 different ways, and that's fine. And adding in social forces into data-driven models, yes, I have a collaborator where we're looking into this.
Brilliant. Thank you. So we are on the hour mark, so just being respectful of everybody's time and yourself as well, Dr. Helbing. Really appreciate you talking today. Really enjoyed this. It was a very interesting perspective. Part of what we're trying to do is get different perspectives of ABM across all the different fields and domains. And I hope everybody else got what I got today, was that perspective from where you're coming from. So thank you very much. So clapping from everybody.